Hey, today I'm talking about ideal current sources, and I'm going to use this video as kind of a nightcap to the last video. This is pretty much just overflowing from the topics that I wanted to talk about last time. So let me write this out. EE 101 episode 8 sources. I'm going to do current source in this video. Okay, now where did I leave off last time? Let me do what I always do lately and just draw us a general circuit element here. All right, now I'm going to introduce the ideal current source, just like how in the last video I introduced the ideal voltage source. And I think in future videos coming very soon, I'll talk about dependent sources. So for right now, ideal current source. And remember, ideal sources don't exist. They're mathematical tools for our circuit analysis, so just remember that. But here is the definition of the ideal current source. Or rather, so an ideal current source or ideal current sources force a specified current to flow through themselves. And much like the definition of the ideal voltage source, this is regardless of the circuit elements you attach to the source and regardless of the voltage that appears across the source. So you can see the parallels between the two ideal sources. They both do exactly what they're supposed to do regardless of the circumstances that you employ them in. So again, they're just total non-idealities. We just use them. They're essentially hypotheticals. When you attach one of these sources to a circuit, it's not a question of, oh, here's my real source and then here's what this circuit does. It's no, assuming I could apply this ideal current that otherwise doesn't affect the circuit, this is how it would behave. And with a voltage source, it's assuming I could apply this ideal voltage without otherwise affecting the circuit. Here's how it would behave. And now, much like I did with the voltage source, I want to give an example of, well, okay, but before I do that, I guess let me draw out a quick picture that kind of captures this definition. So here is the circuit symbol for the ideal current source. And like every other circuit symbol, you may or may not find slight different variations on this. But the circle with this arrow is usually how we denote the ideal current source. And so with the case of the voltage source, there was that plus minus to indicate the voltage polarity, and in this case, there's this arrow that indicates the direction of the current flow. And like the voltage, usually next to it, you'll see some kind of label. In this case, I'll keep it vague in general with just IS, indicating that this current flows through the source. And like the definition says, IS will be maintained regardless of what you attach to this. So if I apply some circuit elements here, and these go off and form a circuit, let's say we've got one here. Oops, let's just do that. Forget about this little line here. And then this goes off and does something. And then let's say we attach this guy like that. And you know, there's a current flowing through these elements and off into the circuit like this. So what you'd actually see is some voltage appear across these two nodes, and we can call it Vs. But the current Is that flows from this ideal source does not depend on Vs. It doesn't matter what this voltage is, what appears. It doesn't matter what you attach to the source and what voltage appears. The same current will continue to flow, Is. And just like the case of the ideal voltage source, this could be some constant, this could be any function of time or frequency. It's just your specified current will flow. Exactly the current that's supposed to flow will flow. And so The next thing I wanted to do was give an example of an ideal current source, or just any current source in real life that the average person can relate to. But really, there actually isn't a good analogy. I mean things that, like, forget ideal current sources, but let alone even real current sources are very rare, or rather, your average consumer doesn't often interact with a current source, or at least they're not aware that they do. So we'll talk about circuits that behave as current sources. We will analyze current sources and use them to analyze and design circuits. But there's actually no good example that I can talk about without a lot more background in electrical engineering before we get a lot deeper into this field and introduce some other circuit elements and other circuit components that will behave as current sources. But there's no just back of the hand example like a battery that everyone knows what that is that I can just talk about. So I think it might do more harm than good if I just introduce something random right now, so I'm not going to. But current sources do exist. They're just not as maybe relatable as voltage sources are. And it's interesting because then when you start to think about real life sources, once you lose this qualifier of the ideal part here, right? Like, let's talk about a real voltage source for a second. I said that it applies this voltage, and then as you draw more and more current from it, that voltage will change. So then it's like, at that point, is it even a voltage source? Like, is it a voltage source or is it a current source? Like, if it can't maintain the voltage that it's supposed to, is it really a voltage source, or is it source and current? Which is it? Or is there really even such a thing as a distinction between voltage and current sources in real life? And that's something you can wrestle with yourself, or think about. That's something that in a lot of cases will be up to you and analyze and decide. But I think there is truth in saying, even though a lot of real circuit components or things like real devices like a battery, even though they don't behave ideally, they're a lot closer to a voltage source than they are a current source, for example. But a lot of times you can find ways to model things either way. I mean, ultimately, if you can model it as one or the other, you don't really care physically what it is. So I think what I'm getting at here, I know I'm talking in circles. What I'm getting at is these ideal sources are just modeling tools. They're just techniques, and they have these perfect properties, and there's room for contradictions, but those things don't matter. Like, you can paint yourself in a corner all you want, but just be wary of the line between your imagination and reality here, or mathematics and reality. And on that note, let me talk quickly about a potential contradiction that exists with the definition of the ideal current source. So let me just draw it like this, and I actually had it drawn like this for a moment before I connected anything to it. But the contradiction actually just exists with the circuit element itself. The ideal current source sitting in a vacuum like this is itself a contradiction, is it not? So what do I mean by that? Well, the definition of the ideal current source is that a specified current flows through it, no matter what, right? And it's interesting because, well, what about the case when there's nothing connected to it? So if you remember from the previous video, I talked about the concept of an open circuit. And so this node right here, you can actually say, and this is the most trivial case, that there's a node on either side of this circuit element. The only problem is only one circuit element is connected to either of these nodes. And so there's actually one circuit element on its own is not a circuit. There's no loop here. There's no path for current to flow. And each of these nodes doesn't see any other element. There's nowhere for current to go in this direction, and there's nowhere for current to come from, to enter. So either side of this ideal current source is an open circuit. And when I talked about open circuits, I said that no current flows through an ideal open circuit. But at the same time, this current source should force some current to flow through it. And so that's the contradiction. But like I just talked about, and similar to the case of the ideal voltage source with the short circuit across it, yeah, you can paint yourself in this corner if you want, and you can let this bother you all day, but just remember, there's no such thing as an ideal current source. And for that matter, there's no such thing as an ideal open circuit. But you just, again, you're walking this tightrope between mathematics and reality. So just remember what we use as tools and what's for modeling and analysis, and then what parts of these circuits actually represent real things. So with that, I think this is a relatively shorter video, but that's okay. I just wanted to cover this topic and kind of wrap up my discussion of ideal sources. So like I said, I think the next video will be dependent sources. So I'll talk about dependent voltage and current sources, and they'll be ideal still. So ideal dependent voltage and current. And yeah, just let me know if this has been helpful to you in any way, or if there's anything that you'd like to see. And other than that, I hope you enjoyed and have a great day.